it works in just, say, in the X direction or the Y direction. One-way system. And so you could provide the enclosure of a long spanning space with a whole series of trusses, say at regular centres in plan. You could have pitched portal frames, which are a one-way system. You could have a series of arches. And finally, you could have folded plates, which span in one direction. And then you have to ask yourself, well, spanning my large span, how far apart in plan should these beams be? Well, I suppose a rule of thumb is that the beam should be between 4 and 8 meters apart, because the further apart your beams or trusses are, the deeper are the purlins that span between those beams and trusses. And so you don't usually want to have those purlins needing to span, more than, say, 8 meters, because otherwise those purlins become really quite deep and quite large. Now, when it comes to making choices about one-way systems, architects tend to use tables like this, where different structural systems are shown along with their spans. And if we look at this table here, which is for timber structures, let's go to beams, say laminated timber beams. Well, first of all, we see that these beams in practice are used to span distances from, say, 4 meters right through to about 25 meters. It wouldn't be sensible to use laminated beams for more than a 25-meter span. And the table gives us what the depth of these beams are, approximately the span divided by 18. Let's look at a truss. Say we've got a bowstring truss like this. Well, normally, from practice, a truss like this would start to be used for any spans greater than about 18 meters. It doesn't make sense to use such a truss for lesser spans. And a truss like this can span from 18 meters right up to 45 meters. And so if you are interested in using timber and you want like a bowstring truss like that, and your span is between 18 and 45 meters, well, this table is telling you that you've made a good choice. And the depth of that truss is going to be, it depends on the weight it is carrying, but say an average weight would be, the average depth would be the span divided by 8. So if you have a 40-meter long truss, the depth is going to be 40 divided by 8. The truss is going to be 5 meters deep to span 40 meters. It's quite deep, isn't it? It's almost 2 stories high to span 40 meters. But, 40 meters is a very long span. We have a similar table that architects use to size reinforced concrete members for gravity loads. And so if you've got a concrete beam, which is poured in place, I'm just trying to get my mouse going. It's hard to see. But if the beam is simply supported, it can span anywhere from about 3 meters through to about 15 meters. And any further than that, a beam isn't very sensible. Typically, its depth is the span divided by 15. So if you have a 15-meter span, your beam will be at least 1 meter deep. At the bottom of this table, we've got information about a dome, a concrete dome. And typically that goes from about an 8-meter span to beyond 60 meters, divided by, say, 5 or 6. And so if you've got a 50-meter dome, it's going to have a rise or structural depth of about 10 meters. So, whenever we steel, well, if we just have a typical steel beam, a steel I-beam, which will have wide flanges, these beams typically go from about 4 meters through to that region. Then ordinary wide flange steel beams might be suitable for you. But if your span is greater, then you'll go to another structural system, say like a truss. Say like take a steel bowstring truss spanning range. A bowstring truss, it would be perfect for you. And its depth would be span divided by, say, about 7. So if it's about 30 meters, your truss is going to be a bit over 4 meters deep. So these charts are really crucial for you to make sure that you choose the right structure for the span that you've got. So for example, about 18 meters, and it probably goes to about 80 meters. So you want to choose a structural system that is appropriate for your span, and use a table like this to work out the depth of your structure. Here's just a close-up look at some of the steel trusses that we as architects use. And this is just, for example, to show that bowstring truss in a bit more detail. This is probably about 15 meters through to about 36 meters. That's the perfect range. Now, I want to give you a bit more information about systems that resist loads in bending and shear. And the most common systems that do this, bending strength and their shear strength. And it's important to note here that both of these elements can be of any shape in section and elevation. Now I'm just going to stop sharing and share my whiteboard with you, because I just want to explain that in textbooks, you know, the trusses are always symmetrical and regular. Like this is a typical textbook truss. And a truss like this is used widely in practice. You know, it's fully triangulated. But I just want to point out to you that if you're going to use a truss like this, I mean, you're basically using a pretty boring structural element. Now, if your design concept was for an ordinary boring roof, then this would be a perfect choice. But remember that you are allowed to transform the shape of trusses and beams to suit your design concept. So say your design concept for this long span is about softness or wave action, something like that. Then you are allowed to design a beam or a truss like that. That could be a timber beam made out of glue laminated timber. It could actually be a steel beam, or depending on the span, it could be a steel truss. You know, perfectly triangulated. So do remember that although most trusses we see are boring, as an architectural student, we want you to have your trusses so that they enhance your design concept. And so you are able to create a truss of any shape and elevation, as long as it's fully triangulated. Although, as I say, this could be the shape of a beam too. It could even be a concrete beam, although it would be very heavy and deep. But in theory, you can have curved beams of any material. You might want to ask me a question about this at the end of my lecture. So let me go back to the main thrust of my lecture. Now I'm going to discuss the different types of one-way systems that I haven't already. And next up is folded plate structures. Here is a typical folded plate roof structure. And you can see why it's called a folded plate, because the roof planes are sort of folded. You could imagine modeling them with paper, say like origami. And when we have a folded plate structure like this, the main span is this way. And so this is the main span of this folded plate. In this case, it's about 30 meters. And so here is the span, and here are the supports at each end of the span. So a folded plate consists of the apex fold at the top, and these are called valley, the folds in the valleys. And of course, it's that folding that gives a folded plate structure its strength. I mean, if we have, you know, a piece of paper without a fold, it's very weak and floppy. But as soon as we put a fold in it, it becomes very rigid and it can act as a beam. So there's a folded plate structure for you. Here is a folded plate gymnasium that I visited some years ago in Hong Kong. And it's made out of reinforced concrete. And so here is the floor of the gym. Here are folded plate walls with folded plate reinforced concrete roof beams. And of course, the beauty of a folded plate like this is that you're just using one material, and it's really quite simple detailing. But I wouldn't recommend a concrete folded plate in Indonesia because of your earthquake problems. This would be a very heavy building because of the weight of all that concrete roof. And so this is a good solution for a country like Singapore, or Hong Kong, which doesn't suffer from earthquakes. If you are in an earthquake zone, this is a far better solution using folded plates, where the plates are like inclined trusses. And so the folded plates probably span 30 to 40 meters across this airport foyer space. And you can see the trusses here. And so they just like lean against each other, just leaning against each other, creating the folds and therefore the folded plate description. So this is an excellent lightweight example of a folded plate. What about pitched portal frames? These are very common. And this is an elevation of maybe a steel or a wooden pitched portal frame. The column, a rigid joint, a very rigid and strong joint between column and the rafter. Maybe a rigid joint here, although that's not necessary. And then we have the column coming down to the foundation. And here is an example of a famous pitched portal frame, the Gallery of Machines in Paris, built out of, it's an early cast iron structure. And it's absolutely massive. I forget the span, but it's, I think it might be close to 100 meters in span, actually. And so you have these amazing one-way portal frames spanning the space, and joining the portal frames are these like rafters, I suppose, and they are supporting the roof structure and glazing on top. And looking along inside this building, you can just see the scale of it, the vast scale, and you can see the way the base of the columns, they taper down, and this is what we call a pin joint here, a pin joint. the column can rotate at the base here. And this is how we would build a pitched portal frame structure. Like here is one of the portal frames here. Here's another portal frame. These are the purlins spanning between the portal frames. And then the roofing goes on top of the purlins. So it's a pretty, straightforward system, but I must say it's not very highly favored by architects. I've never seen an award-winning work of architecture using pitched portal frames. What about two-way systems? Well, the two main types of two-way systems are space frames and shell structures. What do space frames look like? Well, in elevation, they look like this. They are fully triangulated, usually made out of steel. And so they consist of trusses in one direction combined with trusses in the other direction, creating a grid of trusses. And so in elevation, they look like that. Every part of them is triangulated. And we support these structures. We must always have the column or support under one of these joints or nodes. Here's a typical space frame structure spanning a large atrium area in a building in the US. I don't recommend you use space frames often in your designs because the architectural qualities are confusing. There's so many thousands of members, it's hard to understand them and enjoy them. And so I advise my students to try not to use space frames. Here's a close-up of a space frame. Here's the column, a joint, and then the various triangulated members, moving off and away from this joint. See the ball joints that enable many individual members to join at one point. And it's these joints that make space frames quite expensive. And you probably don't see many in Indonesia. There'll be a few, perhaps in the canopies of your 5-star hotels. Then another type of system. So far, I've been talking about systems that rely on bending and shear to transfer loads. Well, now I'm going to talk about two systems that transfer their forces through compression. And so they get their strength through their form. Like arches and shells are strong just because of their shape, their symmetrical shape. I mean, you know how strong hen's eggs are. The shells of a hen are very thin, but yet those eggs are very strong. And it's purely because of their form or their shape. So we've got shells. I think you're very familiar with arches. So here I've got a couple of shell structures. Its strength comes from its curvature, and the shell can be quite thin. This particular shell structure is a dance studio. And I mean, the shell is really elegant. And, you know, this is a very special space. suitable, for a very special function. I mean, you wouldn't use a shell structure for example, a warehouse or a storage facility. Here's some other shell structures. And in fact, all of these are made out of wood. And so this is a ribbed shell. These are the lines of the ribs. And these are other types of shell structures in wood. And so here you can see the timber elements that curve and create the flow, the smooth flowing forms of the shells, covering a swimming pool complex in Germany. And here, covering another swimming pool, is that ribbed shell structure. And you can see all the timber ribs that rise up to enclose really a very beautiful volume, a very beautiful space. And you can see the architect has, thought very carefully about the lighting and creating a very nice, emotional atmosphere in the swimming pool. Here's a concrete shell structure designed by the famous Italian designer, Pier Luigi Nervi. And so here, this is all concrete. Here's another structure, a shell structure designed by Felix Candela, a Mexican architect. And at the edges of the shell, you can see these arch shapes. Well, they require tension members to stop the arches from spreading out and from collapsing. And so all around the perimeter of this particular shell structure, we require these tension beams, just acting in tension to give strength to the shell roof structure. So those were structures that rely on compression. Now I'm going to, I think, finish up with just showing you some examples of structures that mainly work in tension. And these structures are very suitable for long spans. We've got catenary structures and fabric structures. And so as an example of a catenary structure, I want to show you this paper factory in Italy designed by Nervi. And this is a longitudinal section of the structure. You've got these massive concrete piers. There it is, a photograph of it. Another pier. And here is a catenary. It's like a suspension bridge, isn't it? These are cables. It's exactly like a suspension bridge. Here you can see a photograph. And so these cables, they resist the weight of the roof of the factory, and in fact, the weight of the walls as well. And so that means that there's no need for any other structure in this building. And it enables the paper manufacturing process not to be affected by any internal structure. And that was the design concept. The design concept was to just have structure that enhanced the flow of the paper manufacture. And so Nervi came up with this amazing tension catenary structure to support the roof. The other type of tension structure is where we use fabric. And we might call this like a fabric structure. And like here's an example of a very simple fabric structure. It's got 2 masts and 2 connections to the ground. And fabric structures have to have reversed curvature. Otherwise, in the wind, they will flap and they will get damaged very quickly. And so this simple structure here has curvature in one direction, like this, and then in the opposite direction, it has opposite curvature. We call this anticlastic curvature. And so for every tension fabric structure, we need high points and low points, high and low, so that we can get enough curvature in the fabric, and we can tension the fabric so it's really tight as a drum, and then it's not going to flap excessively, under wind gusts. Let me show you a couple of examples. Here's a stadium in Saudi Arabia. This is really a beautiful tension structure. Here's a mast. That's the central mast going up to create a high point. And here's the low point here, created by a compression member and a tension tie. And the edges of these structures have cables, like this is a catenary cable here. And the main structural element is the fabric. In this case, it's woven fiberglass coated with Teflon, the same stuff that we use on our frying pans to stop dirt from sticking. Here's the inside of the stadium structure. We've got valley cables and we've got apex cables. We're always creating the reverse curvature. And so, the spans here are huge, but it's a very sensible structural system. Here you can see the masts creating the high points. They come down to pin joints near the base. And here, and all the rest is really fabric. Here's another interesting fabric structure. The fabric, which curves this way along the building, and it has an opposite curvature across the building, it is supported at the high points by these curved steel trusses, which themselves are very elegant, aren't they? They come down to pin joints at the base, and then the fabric is attached to these trusses and also is pulled down by catenary cables at the edges of the building. And surrounding the building, there's actually a pool of water to prevent people from using knives or cigarettes to damage the fabric, because the fabric is quite easily damaged. So here's some rules of thumb for you for your long span structures. If you're using trusses, the depths of your trusses are going to be the span divided by 4 to the span divided by 15. You would use 4 if your truss was supporting a heavy roof, like a concrete slab. And you would use 15, L over 15, if you had a very light roof on your truss. beams, I usually use span divided by 15. That's a good rule of thumb. So if you've got a 15-meter span, the depth of your beam must be 1 meter. If your span is 30 meters, the depth of your beams will be 2 meters deep, which is a lot deeper than your height. And so that's why it's not sensible to have beams spanning, very long spans. And if your beams cantilever, their depth has to be the span divided by 7. So if you've got a 7-meter long cantilever beam, it has to be 1 meter deep where it begins its cantilever, but you can reduce the depth towards the tip of the cantilever. And if you're wanting to know the structural depths for other systems, then I'm sorry, I can't give you any rules of thumb. Maybe they're not available. You can always look in textbooks, but if not, please use precedents. Find an example of a building using that system and work out the depth from that precedent. So once again, I've given you many systems that are options for you to use in your design projects. And as I said at the start of my lecture, you've got to ask this question: which of those systems is best for your design concept and the program of your building? This is what your tutors and your critics will be asking you. Why have you chosen that structural system? It's boring. Is your design concept boring? No. So therefore you shouldn't use that system. And does that system help enhance the program or the use of your space? These are really the critical questions we start with. So there we are. That's the end of my lecture, my first lecture today. I'm going to pause for questions and comments. But I'm going to give you 5 minutes just to think about any questions or comments you've got. And then I'm going to come back and talk about lateral loads. Oh no, we're going to have a break and do something different. So I'm just going to have a 5-minute break, Ibu Fenty, and then I will come back and answer any questions.
Okay.
Is that okay?
Yes, that is very okay for us. So, ya adik-adik punya waktu 5 menit untuk memikirkan apa tadi yang sudah
Okay, so
dijelaskan.
I'll be back in 5 minutes.
Oke, ya. Tidak apa-apa, Ananda silakan raise hand, nanti ditanyain 5 menit lagi ya. Masih ini, ada break sebentar. Silakan ada yang punya pertanyaan bisa raise hand ataupun ditulis. Boleh pakai bahasa Indonesia juga, ditulis di chat box atau raise hand. 5 menit lagi nanti Bapak Andrew akan kembali kemudian menjawab pertanyaan dari adik-adik semuanya.
rule of thumb is span divided by 15. But I mean, if your tutors in Indonesia tell you span divided by 12, well, then probably you should take their advice. I mean, it's just approximate. And I mean, if you take span divided by 12, well, you're going to be conservative. And that means that when your structural engineer does the detailed calculations for your beams, then maybe he or she will say, you can have a shallower beam depth. But it's always good to make a greater allowance at the beginning. It's better to be conservative. So, but I personally think that span divided by 12 is too conservative. I would recommend span divided by 15.
Okay, thank you, Andrew. I think this is becoming the discussion as well among the lecturer on the previous meeting between Andrew and all the lecturers actually, Ananda. Jadi kami berdiskusi kenapa sih kok beda gitu ukurannya gitu. Kami juga mau menanyakan gitu. Ada satu pemahaman yang dikatakan oleh Andrew tadi juga bahwa di US sendiri bahkan span-nya itu dibagi sama 20 gitu. Kalau dikira-kira mungkin satu dari teknologi yang kita punya juga mungkin akan sangat berbeda dengan negara-negara lain, terutama negara-negara maju, kemudian availability dari materialnya gitu. Dan quality-nya juga mungkin akan sangat berbeda gitu. Jadi kalian bisa menggunakan L dibagi 12 seperti yang kami sudah jelaskan, ataupun yang bisa menggunakan yang L dibagi 15 gitu. Karena apa namanya itu ada rule of thumb, yang penting kita bisa merefer rule of thumb mana yang mau dipakai gitu. Jadi itu yang jadi hal penting ya. Jadi dimanapun nanti Anda berpraktek, kalau misal Anda berprakteknya tarafnya adalah pindah negara gitu, mungkin rule of thumb-nya akan berbeda lagi gitu. Karena kita hanya ingat ya ini rule of thumb, di mana itu bukan kalkulasi yang exact, yang detail banget. Itu cuman kayak general calculation. Nanti yang akan mendetailkannya adalah civil engineer. Jadi kita tapi tetap harus tahu seberapa besar karena itu akan mempengaruhi space yang ada di dalam arsitektur kita sendiri gitu. Jadi Anda tidak perlu bingung mau pakai yang mana gitu, mau pakai 15 apa yang 12. Di Indonesia pada umumnya memang bagi 12. Bahkan ada yang dibagi 10 kadang-kadang karena saking ini untuk precautions. Even Andrew said that divided by 12 is too conservative. But we have another calculation that it is divided by 10. It is more conservative, I think. So, jadi nggak masalah gitu. Anda mau pakai yang mana karena itu nanti pada akhirnya kalau ternyata civil engineering-nya yang akan menghitung apa sebenarnya kalau depth-nya itu seberapa, mungkin akan jatuhnya akan lebih slimmer gitu tadi kata Andrew ya. Jadi seperti itu. Jadi tidak perlu dibingungkan. Kamu bisa pakai N12 ataupun pakai 15 asalkan merefer menurut siapa seperti itu.
Could I just add one more point?
Yes, okay.
If your beams are reinforced concrete, then the cost of your beam is mainly due to the cost of the concrete and the cost of the reinforcing steel. Now, if you have a deeper beam, you need less reinforcing steel, but you have to use more concrete. And so maybe in Indonesia, it's cheaper to have deeper beams which use less reinforcement.
Yeah. So it is very location based ya Ananda. Jadi memang this is based on practice. But again, I think divided by 12 and divided by 15 is not having like a very big gap. Ini besarannya nggak terlalu besar gitu ya dibagi 12 sama 15 gitu. Tapi ya itu sih bisa bisa digunakan dua-duanya gitu. Is there any other question? Ada lagi yang mau tanya? Okay, I think the previous session is very clear, Andrew. I mean, it is very concise, so there's no more question yet. I think we can continue to the next presentation.
Could I just make one more point?
Okay.
Ibi Fenty, what is the design studio project the students are currently working on?
Ah, for this year, they have growing house, right? Is that correct? Growing house? Or is it residential building?
Growing house.
Okay, growing house. So the theme is growing house means that the it's basically two stories like residential building, but it has the possibility to add more stories on it. So that's the project. Yeah.
Okay. Well, I'd just like to ask the students to check their drawings to make sure that the beams of their house have the correct depth of span, say, divided by 12. Please check that you've drawn your beams on your architectural plans so that the depth is span divided by 12.
Yes, thank you, Andrew. That's a very important point because I think I can find a lot of students didn't aware about the depth of their beam. They just draw it and didn't really calculate it. So when I ask how depth is the beam, they were like, um, wait a minute, I forgot something. So I guess they are not really considering the depth. So buat adik-adik ya, ini pesan dari Andrew. Mumpung kalian masih bangunannya masih 2 lantai dan tidak terlalu tinggi gitu, kalian bisa mengecek ulang kembali beamnya itu, baloknya, tebalnya tuh seberapa sih gitu. Apakah sudah sesuai dengan kalau yang sudah dikatakan dibagi 12 itu sudah atau belum gitu. Jadi karena kadang kita lupa nih kalau dalam gambar potongan itu kan terlihat kan ya beamnya. Nah itu kadang-kadang suka ya udah yang penting tempel aja gitu. Biar selesai gitu kan, nggak bisa gitu ya. Jadi kalau di struktur itu harus benar-benar ini. Karena kalau kalian gambar strukturnya benar, gambarnya itu akan jadi hidup gitu loh. Jadi bukan karena tempelan doang gitu, tapi karena strukturnya sudah benar, otomatis gambar kalian punya istilahnya bercerita bahwa this is a building that can be built, not only just imaginative design. So those are the important thing what you have to do. Try to be responsible as soon as possible when you study architecture, because when you have reached for example, at the end of the year, at the end of the time when you study architecture and you are not responsible for your design, it will cause a problematic thing for yourself. So, jadi belajar menjadi responsible pada apa yang kalian gambar gitu. Yeah. Is there any question? So if we don't have any more question, we can go to the next presentation. Ada lagi yang mau tanya? Oh, yeah. We have one more question, Andrew. Silakan, Syahla.
Yeah, hello, Mr. Manager. I would like to ask some question regarding the my project. So, I was when from the previous lecture from you, I showed you my resist report, and then I used shear walls and then moment frames. But I actually used the same structure on my actual project plan. But my lecturer said that shear walls is not nggak biasa tuh apa ya Bu? Tidak biasa
It's
dipakai.
not commonly used.
Yeah,
Yes.
it's not commonly used in two-story building. So what do you think about it? Is it okay that I'm using shear walls to my two-story building, or there are any other? Thank you, Mr. Andrew.
Okay, well, the reality is that in Indonesia, most of your houses use confined masonry shear walls. but because you use resist in your house, you probably used reinforced concrete shear walls. And you are allowed to do that. And so even though it is not usual, there was no reason to stop you from doing that. Like actually, most works of architecture by definition are not usual. You know, architects use their creativity. They use materials in a different way using their imagination. And that's what makes architecture so exciting. So, you know, I think I would agree with what you've done. No problem at all.
Okay, wonderful. Thank you, Mr. Andrew.
I think just keep in mind, Shahla. I mean, Andrew is maybe has a lot of experience in Indonesia, and he is aware that your reinforced shear wall for two-story building is not commonly used in our practice because of the efficiency. I mean, not the structural efficiency, but the cost efficiency becomes the highest priorities when you are dealing with projects, and that's what actually happening in the real project. So there are another thing which is considered as a cost that makes architect to think that it's supposed to be affordable for the client as well, even though we want to like experience more. Jadi mungkin tadi yang dimaksud Syahla memang tidak biasa gitu ya Syahla, karena memang um, prak, setiap dosen punya experience praktisnya sendiri-sendiri, dan dimanapun dia berpraktis itu akan mempengaruhi vocabulary-nya gitu. Jadi kalau dia bilangnya uncommon, ya berarti uncommon gitu. Tapi bukan berarti Syahla nggak boleh pakai gitu. Boleh, boleh aja gitu. Nanti silakan ditanyain aja gitu. Kalau nggak boleh pakai, kenapa Pak? Gitu. Kan secara struktur benar nih gitu. Apakah secara cost efficientnya atau bagaimana gitu. Jadi itu yang menjadi ininya Syahla. Kalau masalah boleh nggak boleh dipakai, kan Syahla nggak terbatas cost efficientnya ya. Jadi pakai aja nggak masalah gitu, Syahla. So, okay. Is there any question? Okay, Shala. So, okay. I think there are no more questions, Andrew. We can proceed to the next chapter of your presentation.
Okay. Righto. Well, I'll see my screen again.
Yeah.
Sorry. Oh, well. Okay. Okay, so now I'm moving on to the second part of today's lecture. Can you see my slide
Yes, we can
and
see.
my mouse? Is my mouse visible?
Yes.
Good, okay. So I've already talked about gravity loads, the structure you need for gravity loads. Now I'm going to talk about the structure you need for lateral or earthquake loads, earthquake and wind loads. And just like I showed you in an earlier lecture, I just want to remind you that earthquake loads are very, very important in your country, just as they are in my own country. You can see that there have been so many earthquakes in Indonesia, and therefore you have to expect all of your designs to experience strong shaking. So what about the structure for wide span buildings? Well, the principles are just the same for any building. It doesn't matter if it's a high building, a short span, or a wide span. The principles are the same. And the first principle is that in each direction and plan, you must provide resistance. As I pointed out in an earlier lecture, if this is a plan and say the building is here, an earthquake can attack at any angle at all. It could attack in the X direction or the Y direction, or at this angle, theta here. And so in order to resist attack from any direction, the principle is that we provide resistance in the Y direction and the X direction. And so in this building here, resistance in the X direction is 2 shear walls, here and here. In the Y direction, 2 shear walls. Or we could use moment frames. That's the first principle. Then when it comes to wide span structures, we still have to remember that if we have a post and beam structure, it is unstable for horizontal and earthquake loads. And even walls of a long span structure are unstable for loads at right angles to the length of the wall. And then for our long span structure, like any structure we design, we've got to choose one of these structural systems for each direction. So you could have like moment frames in both directions. Or you could have a moment frame in one direction and a shear wall in the other, or shear walls in the other. And you can have as many shear walls or moment frames as you need according to your program and your design concept. Now, as you know, shear walls are appropriate in a wide span building. If it's a wide span building, it means that maybe the shear walls are quite heavily stressed, and maybe reinforced concrete is the best material. But shear walls can be of different materials. And as I have explained to you earlier, most shear walls in Indonesia are confined masonry. Bricks confined with tie columns, column praktis, practical columns, and ring balok, tie beams. So here's your earthquake force. It's resisted by compression in the diagonal, and tension occurs in this practical column. But of course, if you're using confined masonry shear walls, you cannot have big openings. And maybe that would be a reason for using reinforced concrete shear walls, because reinforced concrete is a stronger material, and therefore you could have bigger openings in your walls. Then in a wide span structure, you can choose braced frames where your frames are triangulated to give resistance against horizontal loads. In a wide span structure, you can have any configuration, any layout of triangulated cross-braced frames. You know, you could have frames with cross-bracing like this, or inverted V-braced frames, or diagonally braced frames. Or you could have frames where the members, the diagonals, just work in tension. And so these members are very small because, yeah, they just withstand tension forces. And then finally, we can have special eccentric frames where we have these structural fuses that enable the frames to be very ductile, which is very good in earthquakes. So as the architect, you know, you can choose what sort of frame that you would like. Now, if most of your building is in structural steel, like if your roof structure is steel, then it makes a lot of sense to use cross bracing, say, instead of shear walls or moment frames. But it's up to you. It depends on your program and your design concept. And finally, as you know, you can use moment frames to resist horizontal forces. And a moment frame consists of beams and columns connected by rigid joints, very strong joints at each intersection. This is a moment frame. And so when it comes to moment frames, you can have as many frames in plan as you want to suit your concept and your program, and to avoid your columns and beams becoming too large in cross-section. And then for a wide span structure, we have to answer the same question that we do for any building. It's the same question, no matter what sort of building, high or low, wide or short. How much structure do you need? And of course, that's when we go to the resist software to work out, to do a preliminary rule of thumb design so that we can get approximate dimensions for our members that resist earthquake. And then using that software, we can design the dimensions of our columns and beams, or the lengths of our shear walls and how many we need, and so on. Now, all that structure I've just told you about, like shear walls, moment frames, cross-braced frames, all of that structure is vertical structure. You know, like a shear wall is vertical, isn't it? But in all of our buildings, as well as needing vertical structure, we need horizontal structure. And so I'm going to talk a wee bit about that now. We're going to look at this rather boring building here. It's a boring rectangular building. It's got a structural wall at each end, a shear wall, and it's got a moment resisting frame along the two lengths of the building, just 3 columns. Now, if we look at a cross section through this building during an earthquake, it looks like this. The columns bend and the whole building sways sideways during the shaking. It sways or it drifts sideways. And the reason is because of the inertia forces. Wherever there is mass, there is an inertia force. So there's inertia force from the floor slabs, inertia force from the columns and walls. And so this is the view of the forces in section. What about in plan? Well, here are the forces in plan. These are the forces from the weight of the floor slab. Here are the forces from the weight of the cladding, say. And so these are all the forces in the building. And for this particular building, these forces are resisted at each end by the structural walls. And so each floor slab and the roof slab, the roof, it has to act as a horizontal beam, withstanding these horizontal forces and then transferring them sideways down into the vertical structure. So this is horizontal structure. It works horizontally, transferring the forces into the vertical structure. And so here is that same diaphragm. Here are the walls. We can simplify this diagram. The walls represent supports, and the horizontal beam is just represented by a straight line. And so like the diaphragm, the floor slab, or the floor diaphragm, when it acts horizontally, it has a deflected shape like a normal beam, except that it's bending horizontally. Most beams bend vertically, don't they? Most beams bend vertically, but a diaphragm in an earthquake, because of the horizontal loads, bends horizontally. And so the diaphragm has a deflected shape like this. It has shear forces and it has bending in it, with the maximum bending, which would cause it to break, occurring at the mid-span. And so what you have to realize is that the further apart in plan the vertical structure, the stronger the diaphragm must be. And normally your floor slabs are strong enough to act as horizontal diaphragms. And so this is what a diaphragm looks like in a real building. There's the floor slab. Here is a beam, a perimeter beam, another perimeter beam. And so under earthquake, the diaphragm bends, transferring the forces to this support, this shear wall, and that shear wall. Or maybe this is a moment frame into this moment frame and that moment frame. And so if we are using steel structure, like this would be the concrete floor, and this would be the chord of the diaphragm. This is a normal reinforced concrete diaphragm. The floor slab, and this is the perimeter beam that is also called a chord of a diaphragm. And so floor diaphragms can be in different materials. In a wooden building, where you've got wooden floors, the diaphragm would be usually made of plywood, and it can be a very good, strong diaphragm. Here, your timber or wooden floor joists. But for a wide span structure, this is the sort of diaphragm we usually use. So when it comes to a wide span structure, usually the roof will be rather light. Then we have to create horizontal diaphragms using like horizontal trusses. And so in this building here, we hear the earthquake forces acting in the Y direction. They are ultimately resisted by cross bracing at each end of the building, here and here. And so all the inertia forces acting from the roof of this building, they have to be resisted by a horizontal truss, or two trusses in this case. And these trusses, their job is to transfer the forces into this cross bracing here and here. The trusses act like horizontal beams. And so for every wide span structural roof you design, you also have to show this horizontal truss to transfer the loads sideways. So, as I said, for shaking in the Y direction, I have designed two trusses to create a horizontal diaphragm in the Y direction. What about shaking in the X direction? Like in the X direction, we go to the next slide. So in the X direction, for shaking along the building, we need to provide a diaphragm, a roof diaphragm. And in this case, I provided two horizontal trusses. And the jobs of those trusses are to transfer the inertia forces in the roof, due to the weight of the roof, the structure and the cladding. And say you might have a green roof, for example. Then the role of these trusses is to transfer the horizontal forces to this bracing on this side of the building and to bracing on the other side of the building. And that means, of course, you've got a clear span in this wide span structure. There's no structure inside, because here you might like have a post, and this could be like a long beam. I'm assuming these are beams. And so when it comes to the final diaphragm for this building, we need to combine the diaphragms in the X direction and the Y direction together. And so here we've got a truss that's good in the Y direction, and there are two trusses in the Y direction, and they are transferring the forces into these braced bays at each end. And then for forces in the X direction, here's a truss effective in the X direction, and here's the second truss, transferring forces to the bracing that is strong in the X direction. Now, as the architect, you can choose what this cross-bracing diaphragm looks like. If you want to, you could make it like this, so that in the X direction, there's just one truss. And in the Y direction, just one truss. And then you have areas of your roof with no bracing at all. And so you've got to show this bracing in your roof structure that is creating this diaphragm as horizontal structure. And every wide span structure needs diaphragms like this to tie your roof together and to transfer your forces sideways into your vertical bracing. And for wide span structures, the steel bracing is very, very important, and it cannot be neglected. Well, that's all I want to say about earthquake loads. That was quite short, wasn't it? And so now I would like to invite any questions or comments about the structure needed to resist the forces on wide span structures.
Baik, silakan adik-adik apabila ada pertanyaan tentang ini ya, wide span structure. Ini sebenarnya kayak ada dari kelas lain juga boleh bertanya tentang wide span structure. Silakan apabila ada pertanyaan.
Excuse me, Ibu Fenty.
Yes?
Oh, we can't hear clearly.
Oh, okay, sorry. So this is the time for you to ask question. All students are allowed to ask, even though you are not from the structural class. Jadi semua mahasiswa boleh.
The
Ya?
Zoom.
Oh, is my Zoom not working well? Apa nge-lag ya Zoom saya? Oh, oke. Baik-baik. I think my internet connection is a little bit unstable. Is it clear now?
Okay, Andrew, can you hear me maybe?
Yes, I can hear you.
Okay, maybe there's a problem in Ibu Fenty connection with internet. I think we can move the question and or comments maybe from class. Mungkin ada pertanyaan yang bisa ditanyakan kepada Pak Andrew. Sambil mungkin Bu Fenty bisa mencoba kembali. Tadi seperti transformer, Bu. Ya, begini. Oke. Mungkin kepada kelas, mungkin ada pertanyaan tadi terkait yang disampaikan oleh Pak Andrew tadi. Any question maybe?
Just while the students are thinking, I'm going to just share my whiteboard and just give you a couple of examples. Like here is a wide span structure. Say 40 meters by 40 meters. Now say we're using trusses, then usually we would have posts at the end of each truss, and we would have the trusses spanning in one direction to take our gravity loads, like that. One, two, three, four, five. So these are 8 meters apart. So we would have our purlins, spanning that way. Now, if we wanted to, we could have a moment frame at each end of our building. So here are the columns. And here is a beam. And at the other end of our building, we could have another moment frame. Excuse my terrible drawing. These are columns. And here is the beam over the columns. And so in the Y direction, the trusses and the posts, they just withstand the gravity loads. And in the Y direction, for earthquake, the earthquake load is resisted by this moment frame here, 1, 2, 3, 4 bays, and this moment frame. And so we have to provide a diaphragm to transfer the forces into each moment frame. So in the Y direction, this could be the diaphragm. And in the X direction, well, we'll say we've got a shear wall here and a shear wall here. Well, then we would have to create, say, a diaphragm in the X direction. And so now all the forces can be transferred into the moment frames in the Y direction and the two shear walls in the X direction. But there are many alternatives to doing this. Like if you wanted to, you could have the same wide span structure and you could resist the earthquake loads with, say, 4 or 5 shear walls and plan like that. And so that would mean that you wouldn't have any moment frames or shear walls, excuse me, on the sides of your building here. And in the Y direction, if you wanted to, you could withstand your earthquake forces with shear walls or moment frames like that. So there's so many options that you as an architect has. And once again, you make the choice based on your program and your design concept. Like if your program was for a whole lot of rooms here, well, then this might be a good solution because you need walls anyway. And so if you had shear walls like that, we would have to put in ties, horizontal ties in the roof to transfer the inertia forces back into these shear walls. And in the X direction, we would also need ties back into the shear walls. So there are many different structural layouts that are possible for you to use for wide span structures. So I'll pause and see if you have any questions.
Oke, mungkin ada pertanyaan dari kelas? Is there any question from the class? Bu Fenty mungkin sudah bisa lancar kembali, Bu?
Apa ini terdengar, Pak?
Sudah bisa tuh, Bu.
Ini saya matiin dulu videonya, kayak takutnya lagi
Ya.
unstable. Baik, ya bagaimana adik-adik? Apakah ada pertanyaan? Mungkin bisa disampaikan secara bahasa Indonesia juga nggak apa-apa. Nanti saya sampaikan. Ya,
Mungkin ini pertanyaan terkait ini yang bulat-bulat tadi itu mungkin tadi terlewat.
oh, itu penjelasan tentang ini Pak, apabila di situ jadi ruangan gitu.
Oh, I see.
Ya, jadi strukturnya itu kan yang kotak-kotak itu yang di samping-sampingnya si bulat itu, yang lurus-lurus itu. Nah itu. Maybe I think this is it becomes the question from the higher the higher year in our students. Is it possible to use a wide span structure on top of not wide span one? I mean, if we have like a free plan space, actually we design a free plan space on the second floor or the third floor or the top of the floor, the top of the story of the building. So is it possible to use this wide span structure? Meanwhile, underneath we are not using the wide span, so we have like a different type of structure there. Is that possible, Andrew?
Okay. Now, here is a multi-story building. I mean, say it's about 40 meters long. And we're going to have a wide span structure at the roof.
Yes.
Now, this is the best place for a wide span structure because the weight of the roof can be quite small. And so it is quite easy to have, you know, a truss spanning 40 meters carrying a light roof. Now, from what we know, this truss is going to be about the span divided by, well, shall we say 8. So for this building, if we want to span 40 meters, then the trusses have to be about 5 meters deep. Now, it is possible to put a wide span, say at half height of a building, or say at the bottom of a building. But so if we have a wide span here, we have our columns coming down. We have our floors here. Now, say we have this scenario. Now, first of all, the roof structure is very shallow. The depth is like, this is 8 meters. And so divide that by 8. So the depth of this is only about 1 meter deep. And this is the problem, because we've got this wide span here. So we've got two problems. We've got a 40 meter span, but the biggest problem is that this beam here, it has to support the weight of all these columns. And so this beam has an incredibly heavy load on it from the columns. And therefore, this beam is a very special beam. We call it a transfer beam. It's a transfer beam because it transfers loads from the columns. A transfer beam. And because this beam has such massive loads on it, because of the loads from the columns, a transfer beam has to be a lot deeper than a normal beam. In fact, a rule of thumb for a transfer beam is that it should be approximately 2 to 3 times deeper than a normal beam. So if this truss is 5 meters deep here, if we want a truss here, it has to be 15 meters deep, which is almost impossible. But it is possible because, for example, we could make a truss like this. So now this is our truss. This is our transfer truss. Okay, it's got to be at least 10 meters deep because it's carrying the weight of all these columns. And so this is the problem if you're having a wide span within a multi-story building. It's always better to have a wide span at the top, then it's not a problem. But if you have a wide span at the bottom of a multi-story building, then people have to walk through these trusses. You know, like here's a person walking through the truss. And there are quite a few buildings in the world like this, where you walk through the trusses that are creating these transfer beams. So does anybody want to further this question?
Paul, is it still structure? Isn't it?
Is it steel structure?
Andrew. Oh. I'm so sorry. Andrew, is it still structure?
Yeah, but in theory, it could be concrete too.
Okay.
In theory, these members could be reinforced concrete. But normally, we would use structural steel. So what I've just told you about are transfer beams. These are beams that support the weight of columns and are so much deeper than a normal beam. And so as you can see, from an architectural point of view, there's a great penalty to have your wide span here. But there's no penalty to have it up here.
Okay, thank you for your explanation, Andrew. I think from now on, I hope that this class understand why are you should try to avoid putting the wide span structure on the floor when it has to carry bigger load, like the like the right hand side of the image here, because by from Andrew explanation, then you can understand how it affect your building and how it affect your design as well. It is easy to draw like a free plan area underneath the multi-story building, but then you have to realize that the structure needs a great cost of toll on it. So it must be deeper, it must be bigger, and it will be very bulky. Is that what you want? So it depends on what you design. But again, that's why we didn't ask you to move it because it's impossible to be built. It is possible, but it costs a lot of money and energy, and it's not efficient for the area as well. So this, your space will not be efficient as possible. So those are why we are trying to suggest you, maybe not today, not this studio, because you only have like 2-story building. Kalian cuma mendesain dua lantai. Tapi biasanya ini akan terjadi in the following year. So before it happens, we would like to make you aware of these consequences, so that you understand why you should put the wide span structure at the top of your building if you have multi-story design. So those are the this question is actually just triggering you, because I believe that you haven't got any clear idea when you should use this wide span at the moment. So jadi ini kayak karena kalian mungkin belum kepikiran untuk pakai wide span di project kalian gitu, sehingga nanti kedepannya itu pasti ada possible penggunaannya, sehingga mungkin tadi saya tanyain dulu gitu. Mungkin dari sini ada lagi pertanyaan dari adik-adik? Okay. I think it's clear, Andrew. And I think students are trying to get to understand about this wide span structure because they haven't got this type of building yet. But as far as I understand from your lecture, this is very simple explanation, and I think students are easily to follow this. The following week, they will have to study the architectural objects that has this wide span, and those the time when they will understand when and how they use the wide span structure. I think I would like to thank you because you have given us so many knowledge about structure, and I'm very delighted that you explain it in a very simple way so that students understand well. Because as I mentioned before in the workshop that we have firstly met, structure becomes something that is very scary for students, especially in architecture, because they just don't understand what is the basic rules. While in the third, I think students can realize that from all of your explanation, everything is actually very basic, and they can understand those basic and then apply it to the more advanced one. So that is very useful for us. Pak Iwan, mau ini?
Yeah, I have the same opinion with you, Bu Fenty. Thank you, Mr. Andrew, for your lessons.
Okay.
Welcome.
It is very nice to have you here, Andrew, because again, it breaks down the barrier that actually structure is not that complicated. So, and it can be learned from a very basic explanation. Ada mungkin yang terakhir ya adik-adik, kalau ada yang mau nanya, baik dari yang kuliah yang hari ini maupun yang sebelum-sebelumnya, ataupun dari yang sudah pernah mencoba resist, ada pertanyaan, saya beri waktu terlebih dahulu. So I will give the time for them to ask if they have question related to your lecture, not only today's lecture, but also the previous lecture. Ada yang mau bertanya?
Okay.
Okay, I will.
Ya, Bu Fenty. Mungkin saya memberikan tambahan. Mungkin sebentar. Kok suara dong? Ya, mungkin ini kepada semua peserta kelas ya, kelas ABQ. Mungkin selain kita mengucapkan terima kasih pada Pak Andrew telah memberikan materi selama 3 kali pertemuan ini, dan saya rasa ini sangat luar biasa karena materi structure ini dihantarkan dengan sangat-sangat simpel kepada kita dan kita mudah untuk memahaminya. Dan ini opini dari saya berdua ya, saya dan Bu Fenty. Mungkin kami berdua ini juga dulunya sama seperti kalian. Kita juga memahami struktur dan momoknya juga sama, saya rasa ya. Tetapi di satu sisi bahwa penjelasan dari Pak Andrew ini memang benar-benar clear dan bisa dipahami dengan mudah. Beda kalau kita hantarkan sistem struktur tadi dengan momen inersia ya, sudah dibayangkan saya hanya membawakan diagram seperti 10 tahun, berapa tahun yang lalu ya, 15 tahun yang lalu ya, momen inersia seperti itu, dan saya tidak tahu sebetulnya yang dibicarakan itu apa gitu. Jadi saya rasa kemudahan ini tolong dimanfaatkan dengan baik. Buku dari Pak Andrew itu juga bisa dibaca dan mudah dipahami. Saya rasa dengan basic Anda di semester ini, untuk kedepannya nanti kita mungkin bertemu di PA 2, 3, 4, 5, Anda sudah memiliki pemahaman struktur yang lebih baik dan lebih matang. Mungkin lebih matang dari kita waktu dulu kita di era kalian, di saat momen-momen seperti kalian. Seperti itu. Ya, begitu Bu Fenty.
Baik, terima kasih Pak Iwan. Yes, I think this is very important knowledge that you have a good understanding on structure, so that you are confident enough to design your building, no matter how is the shape of your building, how is the form of your building, you are confident enough to mention the structure that you are using. That's what we are trying to enforce by inviting Andrew here. So you are so lucky to know him earlier before us, because we knew him after we became lecturers, so it's quite different with you. I think, is there any question? So before we, I think we came to the end of the lecture. Kalau ada pertanyaan nggak? Kalau ada yang mau tanya, silakan raise hand atau tulis di chat.
Sedikit satu kalimat dari saya, Bu. Lagi mumpung tadi separuh dari kelas ini ikut kelas saya.
Ya.
Ya kan, dan kelas Bu Fenty juga untuk metode. Jadi seperti yang tadi kita bicarakan, untuk force base bisa jadi struktur, bisa jadi salah satu bagian yang di-force-kan ya. Jadi pemilihan struktur yang bagaimana menjadi salah satu parameter bagaimana desain bangunan itu didesain seperti itu. Sehingga pemahaman kita terkait struktur, pilihannya bagaimana, itu menjadi satu yang penting untuk bisa ditetapkan di awal seperti itu. Dan resist software-software tersebut bisa membantu kita untuk mencapai keputusan yang tepat dan sesuai dengan kasusnya masing-masing. Yeah. Begitu. Thank you, Fenty, and thank you.
Yes, and resist has helped our studio becomes better, because some students cannot justify the structure, but when we introduce resist, they are able to use it very well for the multi-story building in the third year students. I think you have lecture as well previously for them, so they are using it very well, and now we are happy to have it, because I think it is very easy rule of thumb, and it is very robust, so we are confident with the structure as well. So yeah, do you have any I think sentences for our students in learning structure?
I think that it's important for you students to understand the principles of structure, but it's not necessary to do too much calculation. Maybe just a little bit of calculation, but you should try and really understand the principles so that you can apply your knowledge in your design projects. The reason for learning about structure is so that you can integrate your structure with your design concept. Because if you don't do the preliminary design of your structure, a civil engineer will, and he or she probably won't be able to integrate it nicely with your concept. So it's very important that you have enough structural knowledge so you can do your preliminary structural design, and then the civil engineer, you know, will discuss it with you. You will refine it, and then the end and final product should really enrich your architecture.
Okay, thank you, Andrew. Okay, class. Today, that's the end of Andrew's lecture. Thank you again, Andrew, for coming to our department. It is very nice to have you here, and I'm very glad that you are willing to give our students lecture not only once but more than once, which is really great. I could not imagine that you didn't help us throughout this pandemic situation and try to make this course become more interesting. So thank you very much. It is our biggest honor to have you here.
Well, thank you. I've enjoyed being with you.
Okay, Andrew. I think because this is already late night in New Zealand, thank you for coming today. And I would like to say Merry Christmas for you because it is coming maybe 2 days after today, right? In Friday. So Merry,
It is.
yeah. I get lost
Yeah,
of
thank
the
you.
day. So have a
Thank
nice
you very
holiday.
much.
Yeah, have a nice Christmas as well, and see you soon in other forums with me and Pak Iwan as well.
Okay, thank you very much, and all very best wishes to all of you students. I hope you have a very good career in architecture. So, bye.
Bye bye, Andrew.